Okay, I think we should start. So welcome to the second lecture on deep learning for NLP. Happy to see so many of you here, which is great. And today, okay, so any questions to the last topics, anything which came to your mind and you would like to ask? This is great. Any organizational questions which we didn't talk about at whatever, Discord, Moodle, and stuff like that? Everybody's happy with how things are so far. Discord works for you? Okay, cool. Great. So you might have asked, well, what about the exercises and homeworks? So this is in doing. I guess the first exercise will be ready next week because we have a task force preparing them. And the homeworks, so what we discussed so far, there will be roughly 3, maybe 3 to 4 homeworks overall. Last semester we had 6 and it was an overkill. It was just too much. So we thought 3, maybe 4 homeworks will be the best thing to do. Okay, so these were the orga things. So stay tuned. And today we're going deep, and not like deep learning, but we're going deep into the basics. So why? So let me start with sort of motivation. And I'm going to ask you, who of you, because there's some people who had some machine learning, so who of you knows stochastic gradient descent and backpropagation? Raise your hand. Okay, that should be like a half, a third. Great, nice. Who of you ever implemented this thing from scratch? 1, 2. Okay, cool. Wow, that's great. I'm going to ask the rest, why not? So those of you who know these things, why you haven't implemented them from scratch? It's a really curious question, yes.
Because there are existing frameworks already.
Okay, there are existing frameworks and they make our life easier. Exactly. Anyone had a different reason for why not doing this from scratch and relying on existing frameworks? So I tell you mine. One reason was that, and the second was I found it super complicated. Like why the heck should I do this? The mathematics and stuff. It's like I don't understand it at all. So I'm gonna use what's out there. And actually, understanding things under the hood makes you actually understanding things better, and implementing things makes you that understand even more, right? So those of you who implemented it from scratch, was it a great exercise for you to learn how things actually work under the hood? Was it? Is there somebody who kind of hesitated there, who said well, I shouldn't have done that? It's not the case. So that's great. So the goal of this lecture is to go deep into the core of deep learning, and not even touching deep learning and neural networks, but understanding the mathematics behind and how things can be implemented from scratch. So you can, after this lecture, you should be able to implement the backbone of deep learning and training neural networks basically by your own, and understanding mathematics behind. That's the goal. Okay, it's kind of challenging, so I don't know how, hopefully it will work out. So I'm not a mathematician, I'm a computer scientist. I used to hate mathematics before I kind of understood that mathematics is just it's a weird language. you know, and they have like so many weird kind of so to say, speaking of the same thing in very different languages, as we will see. Okay, so if you hate what you see, you can leave. That's fine. You know? But I guess there's a deep need for understanding. So let's dive deeper. And what we won't be covering here today. So we won't cover the abstract mathematics. We won't cover set theory. Okay. But if you want to understand mathematics, what I learned from mathematicians is like you have to understand set theory because everything can be expressed in terms of sets, which is the assembler of mathematics, you know, but it kind of sucks because it doesn't give you any advantage of being faster. Like if you program something in assembler, it's faster than in doing in Python. If you do mathematics in set theory, yeah, who cares? So you should know something of set theory. So we have sets have elements, there's no ordering, and we have ordered tuples. That's enough for us to know. We won't cover number theory because we know there are some, you know, there's some natural numbers and there's real numbers. Okay, so we have real numbers. This is given, and there's this weird thing like infinity. So yeah, okay, that's a weird animal, but we kind of assume there's infinity and as a reason for things. We won't cover sequences and limits, right? So you should kind of know what sequences of real numbers are and what are the limits, because limits are the backbone of derivatives. Okay, so everybody knows what a limit is. Is there anyone in the room who doesn't know limits? Okay, great. So what is important to know? Okay, what is these weird symbols? So R squared, this is the set of real numbers, and it's basically a tuple of, you know, two real numbers. So a vector or a tuple, two-dimensional vector. Okay, so this is like the simplest thing that we start with. Okay, and what are the problems we're going to solve? Well, what are we interested in the first place? So we need to learn how to minimize functions. You know, so this is basically we need to build the tools in order to train and understand neural networks, and one of the part of that is minimizing functions. So what does it mean? We want to find a minimum of any function. What I'm showing here is a function in like it could be y is something of x, right? So this is the plot, this is the x-axis, this is the y-axis, just a standard thing. So what is the minimum of any function? How do you find it? Yeah, so you can say, well, I'm gonna look, you know, I'm gonna have a look at this chart, and the minimum's right here. Yes, I can see that. Well, this is beautiful, but you can't do that, right? Because you don't see the function. You have the prescription of the function, and typically you cannot plot it. I mean, if it's easy function, you can do it something which you learn in the high school. So you can do, you know, all these derivatives and second derivative and blah 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 equals to 0. Yeah, for easy function, that's easy. That's what you did, I guess, in the high school or in some mathematics. But for complicated functions, you will see it's not trivial, and it could be super cumbersome to actually try to find the minimum. So how can we solve this problem is, well, okay, if I ask you, here's a function and find me the minimum, what, as a computer scientist, what would be like the first thing you will try? The most stupid idea to try to find the minimum of a function. You can evaluate the function and you find the output value. What would be like the super easiest thing to try? You are first.
Try a lot of different random guesses.
You would try, exactly, you would, no, don't laugh. I mean, you would try random guesses, right? So you would say, okay, let's pick this X. Yeah, okay, why not? Let's pick this one. Yeah, let's pick this one. Okay, does it guarantee anything? Yeah, not really. Any other idea?
You look at the neighbors, which is lower. So you start at the random.
Okay, so you would, I see, you would start here and then just look at neighbors and then see. Okay, that's already clever. Something even much worse. Like brute force. I would try all x values and see, okay, for all x, where is the minimum? Yeah, that's the brute force search. It could work. It can't work for unbounded functions. If this were like to infinity, well, then I'm doomed. I cannot try all the real numbers. But I could. So this is like the most stupid thing to try would be a brute search. So we should do any better. The random thing, why not? I mean, I guess it should be something in how's it called? The genetic algorithms are using random kind of function optimization. Why not? We should try something better. And the neighbors, yeah, that's a good idea. We're gonna utilize the curve of, you know, the kind of how the function looks like, the curve. So, but first, what is a function? So we're using the Euler's notation, which is, yeah, we have some arbitrary but somehow standard naming conventions. So we're saying X, the input, Y is typically the output, and F is the name of the function. So we write something like that, right? I mean, this is not rocket science, right? This is Euler notation. What we are saying here is that we have this function from R to R. So it's a mapping from one set to another, and we call this domain, and the other we call codomain, right? So this is like a little bit of terminology. This shouldn't be surprising. I mean, most of that shouldn't be surprising to you, but I'm trying to cover everything to have everyone on board, so that if we are talking about something, that you've heard it. So this is clear. We're using these functions all over the place. Now we have a thing when we have two functions. So we have this function f from reals to reals, and we have a function g from reals to reals. We might stitch them together, right? And we might compose them. And this is the very weird operator, which is kind of saying, I'll take so this is the circle operator, the function composition, and it's saying, I'm first evaluating on f, and then I'm passing that to evaluate to g. Okay, so it's like nested function. You put an argument into the g, but you first evaluate f and then turn to g. So basically nested function. What could be a nested function? For example, y is, I don't know, 2 times x squared. So this is one function inside, and this is the other outside, okay? What can be misleading here is this kind of very weird operator, this circle. So this is how people somehow describe function composition, and you say like, what's coming first, G or F? Actually, I don't remember it. I never remember, so I have to look it up on Wikipedia. So if you see the circle operator, it's function composition, and some people are using that for describing nested functions. I think this is much clearer, right? I mean, you first evaluate the inside and then the outside. Okay, everybody's with me? Awesome. Good, so we know what function is, at least one function from reals to reals, so single variable input and single variable output. And now let's move to some geometry a little bit. So what is a line? Okay, what is a line? I mean, line has a definition. It's very cool. So in a Cartesian plane, lines are characterized by the equations, and every line is a set. Okay, here we're coming to the backbone of mathematics, a set theory. So a line is a set of all points whose coordinates x and y satisfy a linear equation. So this is why it's called linear equation, right? So we have x and y's, and we have some w1, w2, and w3, which are called coefficients. This again shouldn't be surprising, because everybody should somehow know from the high school what is a linear function. So this is a linear function, and a linear function describes a line. It's a set of points. Okay, cool. And they have some properties. Okay, so this shouldn't be surprising, right? Is everybody's on board with me? Lines is a set of points, and it looks like that. So this is a line. Very good. We don't typically use this kind of set-oriented definition of a line, but instead we're using the so-called slope-intercept form. So slope-intercept form is what we know as basically a function of a line, which is y is equal a times x plus b. And this a is the slope, and this b is the intercept. So this is a simple linear function of one variable, one random number, one real number in and real number out. And if we plot a line here, so this would be like some of our lines. For example, y is, so a and b would be some actual real numbers, and we would have this line. What is interesting is what is slope. So it has a meaning. This slope has a meaning. And if I ask you what is a slope or steepness of the curve, I'm thinking in how, if I'm staying here, how steep things go, and how I perceive steepness is not a real number, but as an angle, right? I mean, it's natural to me kind of see steepness of angles between 0 and 90 degrees. If you drive a road, there's like 11 degrees steepness, then you pay attention to how we drive. And there's actually a cool relationship between this number, this coefficient, this slope, and the angle here. And if you come back to trigonometry and pick a triangle here, then the rise over run is the tangents of this angle, right? So there's a relation between the slope and the angle, and this is a tangents, right? It's kind of cool because then I can understand if I see a slope of a curve as a, it's a real number. It could be anything. It could be between minus infinity to plus, well, could be infinity? I don't think so. So something between almost infinity and minus infinity and plus infinity. But I can transfer it into an angle, and then I see, okay, yeah, well, this is like this going that up and that down. Because if you know tangents function, then or arcus tangents, then you can transfer between these two. So if we talk about the slope of a function, then it's a coefficient, like the slope coefficient, but it also has something to do with the angle. Okay, any question? Sounds great. Everybody's with me still. It's a high school mathematics, so it's no surprise. I mean, we shouldn't be doing rocket science here, but building up, really from scratch. So we have lines, we have functions, and now what we want to do in order to minimize the function, we want to approximate a function by a line at a point. Why is it good? Well, because it helps us to find a cool way to find the minimum of the function later on. But how can we approximate a line at a point? So let's pick a point C here, and I want to approximate. Let me come in here, and here I want to approximate a function by a line. So this would be like a tangent, okay? And how can we do that? Well, you can pick a little bit different. You can pick a little bit different point nearby and just make this difference smaller and smaller and smaller and smaller and smaller and smaller using trigonometry, and you end up with this limit. So this is a definition of the derivative of this function f at point C, right? So we pick this point, and here, this is we can approximate by a line. And this derivative at this point is telling us the slope, right? It's telling how steep we go, okay? So derivative is the best linear approximation of a function at a point, and it's telling us how fast the function changes there. Okay, everybody's with me? Any questions to derivative? So who hasn't seen derivatives before? Great. So this is no surprise, right? But just think about it. Yeah, I mean, I can understand the slope. I can approximate a function by the line, and the line is the best approximation of the function at that point. And I'm using the derivative for doing so. And it's telling me how fast the function here is coming up. And I have the exact number. And this will be something like, this function will be actually exactly the derivative at point C times, how is it? Oh, sorry. Is it like x? F derivative of C times x plus fc. Is it possible? Like Taylor expansion, is this correct?
Minus C.
X minus C, exactly. Thank you. Yeah. So let me just do it again. Oops. So this would be x. Oh, what is this? Oh, come on. Ah, yeah. What did I do? Okay. Oh, sorry. So it would be x minus c plus f at c, right? This is the Taylor expansion of a first degree polynomial of Taylor expansion. So this is the exact, and this is the slope, right? You remember the function we used to have this as a. So this is telling me the slope. So it's telling me, how steep is the function changing, or the line approximating function changing at that point. Any questions? Great. So now we have the derivative, and we know what's the derivative of the function at the point. So, and we have the definition, and remember, so we have derivative, which is giving us the value at point C. So it's always bound to a certain value. If we want to compute the derivative here, we would need to compute the limit again, and just, it's boring. So maybe what we want to do instead is to have a function which takes a differentiable function f as input and produces another function at output such that Well, the other function evaluated at c equals to the derivative of f at this point. What does it mean? So an example, let me see, maybe I have an example later on. No. So an example would be, we have that, so f is, I don't know, x squared. And what's the derivative of x squared? Okay, what's the derivative of x squared? What is f prime? Say loud, yeah, say loud. 2x, yes, thank you. 2x, right? Here we have a little bit of this c and x and so on. So basically we want so this would be the function f, then we would have g such that it's 2 times c, because we are changing variables here, right? We would say, okay, the function evaluated at c is 2 times c, which is this derivative, okay? But we typically don't change variables, so we typically say, yeah, well, actually, the derivative of f is 2 times x. So this is what we typically do. Like, we don't care, this is like one variable and the derivative is another variable, and we call them x. Although they are different kind of things a little bit formally. Okay, so everybody's with me? Like, what is the derivative? So we can compute now. So this is cool. We can now compute derivative for each point of this function. So what we plug here will give us derivative of this function at this point. Okay, so this is like derivative computing function, right? Why I'm saying this? Because then we're coming into the hard part of mathematics, which is the notation, and the notation is awful, I'm telling you. Because this derivative computing function, you can write it as d to the dx, and this is not a fraction, this is just one thing, right? So this is not a fraction. This is just how you say like d to dx, and then you plug in the function and compute the derivative of the function. Like here, so you say, derivative of this function f, but then the notation is like inconsistent, it's horrible, because you can write df over dx, but it's not a fraction, or dy dx over dx, and they mean all the same thing. This is the derivative computing function, and you can write it in many different ways. Here you have to choose x, although maybe there's no x in the function. Here you have to choose y and x and so on. So it's really ugly. So what you need to understand that all these are somehow equivalent, and it's just this horrible notation, which makes it kind of clumsy if you don't know what's behind. Okay, so this is one lesson learned. If you read a paper about derivatives, they will use like 20 different ways of writing this function, and they might be mostly equivalent. So it's arbitrary decisions, like speaking 10 languages about the same thing. Okay, any questions to this? Let's move on. So we know how to compute the derivative of the function. Okay, you're still with me? Why we need this? We want to minimize the function. So we want to find the derivative because it will tell us something about the function later on. Well, if the function is easy, like that one, like x squared, yeah, that's fine. How about we have something more complicated, like sinus of x squared? How can we compute the derivative? Yeah. What do you have to do to compute the derivative of this function?
So it consists of two functions, one is sinus and the other is squared.
Exactly, yes.
The inner function and multiplied by the outer.
Right. So we have a compose function here, and there might be some special treatment of that, and it has a name, and it's called a chain rule in English. So there's a chain rule, and it's saying if we have two functions which have derivatives and they're nested, so first fx is inside gx, or f is kind of the input to g, then we take the output of fx, plug it into the derivative of g, and multiply by the derivative of fx. This is the chain rule. Okay, everybody heard of this chain rule before? How to make a derivative of nested functions? If not, make it your friend. Now, chain rule. Okay, so you evaluate the function fx, make it to g, derivative, make a derivative of g and multiply by the derivative of the fx. This is the chain rule. And by the way, here we're using the this prime thing like f prime x as a derivative, and not this dx of f. So we have two different notations. So here I'm showing you the Lagrange notation for derivatives of function. I think you know this from physics, right? If you do physics, they're using like this prime. Is it true? Anybody had some physics before? Well, I used to add one before, so this is what people are, I guess, using. So the prime. I'm gonna show again the same nested function like the chain rule when we were using this kind of ugly notation of the nested functions. So you've seen it at least once, and this is the same. So basically, we're saying, okay, I'm first computing f, plugging it into g, the derivative of g, and multiplying by the derivative of f. So these are equivalent, right? This is the same thing, just written in different language. Here we're using this operator, the circle thing for function composition. It's the same. And we have one more, which is the most awful notation I've seen, but it's like, old API. It's been here for 250 years, 300 years, and nobody wants to ditch it. So we're still using this API and writing derivatives, using this notation, which is the Leibniz notation, 1700 something. And again, we have a function composition f from f g has input fx, and then using this fraction, which is not a fraction, for derivative of h, then the chain rule is multiplying these two things together. Okay. So basically, all of them are equivalent. Yes. Yeah, that's a nice. Maybe I had 3 and I just like, no, it doesn't fit the slide. No, that's typo. So thanks, I'll fix that. Any other question or comment? So I guess we can do like a little bit walkthrough example, because it's important to understand the notation and what we mean by computing this nested derivatives. It's super important for us for minimizing functions, right? So we have here a composed function, which is y is e to sinus x squared. Okay, cool. So it's a composite of 3 functions, and we can just give them names. Let's give them names, okay? So we start here. So the x squared will be function h, and the output of that will be v. Okay. Then the sinus thing will have name g, and the input of the sinus is x squared, which we kind of said it's v. Okay, so it's v sinus v, which is the sinus. Okay, cool. So we gave it names, and then the exponent function, the e to something, is this function, and we said this sinus x squared is the u. Okay, so what we're just doing, we're giving in names, so it's easy to see the chain rule. Okay, everybody's with me with that? Cool. Just giving names, arbitrary names. This is my decision. I said like, okay, this is gonna be called u, and it's gonna be called g, and it's gonna be called h and v. So then these 3 functions have derivatives, which we can compute. So, and here comes the ugly notation. I'm using both. So here's this Leibniz notation, and here's the Lagrange notation. So the derivative of function f, which is e to u, is, what is it? What is derivative of e to something? E to something, exactly the same. Yeah, this is great about e. So yeah, so this is the derivative. E to something is e to something, so derivation of that. It's a beautiful function. And now, okay, so we have the derivative here, and I'm plugging here, because u was sinus x squared, so I'm plugging in here. So we have the derivative of y of the function f, or I can write dy to du, using this Leibniz notation. Okay, everybody knows how we did this? So we basically took this function and make a derivative. And e to u, derivative of that is e to u. E power u. Okay? Cool. The next function was the u is g of v, and it's a sinus, and somehow you learned at high school, like derivative of sinus is cosinus. So we have now the derivative is cosinus v, and then we plug in the v. So this will be cosinus x squared. Okay, so we kind of, this is also, we have derivative of that, and then the derivative of x squared. Okay, we had it already, so it's 2x, right? So we know. So now we have derivative of each of these functions. Okay, what is interesting here, that each of the derivatives is using the output of the previous function, right? Because x squared was the function before, and here sinus x squared was the previous function, right? Yes.
I don't understand why we don't use the chain rule now.
We do use the chain rule. Well, we're computing the.
We say that e to the power of u is the derivative of e to the power of u is e to the power of
Yes.
u. So we're assuming that u is.
We're kind of substituting and making this function simple. That's the point, because they're composed, right? They're simple functions composed together. And before you apply the chain rule, you have to understand each of these functions and their derivatives to the input. This is the first thing I mean, if you do it per hand, you say, okay, sure, I know what is e to u is, and then I'll go deeper. Okay, I'll ask you in 5 minutes. Okay, for that, right? So we now know all these derivatives for each of these functions, and now, so this is repeating again, you know, from the previous slide. We computed just before, and now we can use the chain rule, and the derivative of the whole function at point A is the product of these three derivatives, which we computed before, evaluated at a particular points. Okay, so x is A. I'm evaluating this function, then this function times this function. So this is the chain rule, basically. I mean, you would do it like naively, but we do it like explicitly here by applying really the chain rule for these simple functions. Okay, does it make sense now? Great. Everybody's with me now. Still, I know it's after lunch, and mathematics after lunch is really terrible. I'm really sorry about it. I'm recording this and put it on YouTube so you can rewatch that. And there's billions of sources on the internet to do this. I'm doing my way here, which I hope will kind of enlighten some of us and help us to understand more. If you know it already, the better. So you get a like different view, or maybe you're kind of reaffirm your knowledge. Okay, so everybody's with me here. We took simple functions, make a derivative, and then just make a product of 3 of them to get this derivative for the whole thing. Okay, great. So now we know how to make a derivative of a complicated function, because if you look at this function, well, this is not x squared. This is something very weird. It's actually 3 minus sinus 2x over x. Can you make a derivative of this function? 3 minus sinus 2x over x, just per hand.
Yeah,
probably, yeah, it will take some time, and you would have to do this for each of the function, take a derivative, and then make a chain rule, right? So now we have a really good way how to do it in a structured way. Okay, that's the point. And now we want to find the minimum of the function, and we don't want to go like the brute force, and we're going to take into account the slope of the function at each point. So what we want to find is such an x that minimizes this function. So this is the we call it x hat with a hat here. This is some sort of like estimate, right? And we're going to use gradient-based optimization, and what we need for that is that we can evaluate a function for any x, right? So we can evaluate it at any point. We know what the value of the function is, and we can evaluate its derivative for any point as well, right? So now we are much cleverer than before, because before that, you know, for the brute force, we just needed what the function value is at any point, and we can just go one by one and try and find the minimum. Now we know more about the function because we know not only the value at each point, but also we know, you know, the slope of the linear approximation of the function. How is it going to be helpful? Quite a lot. Because we start somewhere, we pick a random value of x. So let's, I don't know, let's start here. Okay? Now we evaluate the gradient here, not the gradient, sorry, the derivative here, the derivative, which is the slope of this linear approximation. And it will be some number, something between here, some positive number, right? And then we're gonna say, okay, this is the direction and strength of change at this point. So this was like x1. And then we're gonna take this gradient, this derivative we just computed, multiply by something, some small constant, and subtract from the actual value. And we arrive at the next point. What exactly it means? So here we have some positive number, we multiply by a positive number. So we have some small positive number here. And we do x1 minus this small positive thing, which moves us somewhere here. And if this eta constant is small enough, we took a step to something which is smaller than our previous position. Okay, so we are somewhere, we look basically, I have just one direction and I'm staying at a point. And I want to know, okay, in this direction, it's going down. And I make a step. So the more, the steeper the steeper the slope is, the farther I go. Okay, that's basically it. Because if I'm looking for a minimum, if the slope is just very tiny angle, I go just a little bit step because I don't want to overshoot, right? If this is big, I'm going much bigger step. And I repeat this whole thing over and over. And if I decrease the number of eta, this is called learning rate, I will find a minimum point. It won't be the global minimum. It will be maybe a local minimum, but I can come there using much fewer steps than just simple brute force search, definitely, or some other methods. Yes.
We already have the derivative. Can we just mathematically solve for the minimum point?
Yeah and no. You can mathematically solve, absolutely, right? So remember what you just said. We have a derivative. Can we just solve the derivative as at high school, like equals to second derivative? No, the first one equals to 0. Then the second, if it's positive, then it's minimum maximum, right? Yes, for simple functions, absolutely. I'll ask you in 5 minutes. Okay? Yes. Yes.
Isn't it supposed to be like f of xi plus 1 instead of xi plus 1?
No. Why not? Because we're searching for the x. So we want to find a point where the function will be smaller than at point. So we are at point x1. X1, yes. And if we use this gradient, this function, then the point x2, which will be this one, let me see. The point x2 will be smaller than x1. So fx1 will be smaller than fx2. So we're moving on the x side, and the gradient is telling us where to go. Like, should I go left or right? And then, because you're staying on a hill somewhere, on a slope, and you see like, well, I have to go this direction. Then my function will be smaller there. So I'm going there. And how much I'm going, this is the strength, the strength of the slope, or the strength of the gradient is how far I should go right now. I'm changing the x, right? Because that's what I want to find. I want to find this x here down. So I'm changing the next x where I'm going to evaluate. Okay, I'm here. What's my function? What's my derivative? Okay, I have to go here again. Does it make sense? I'll try. So I have an example on the next slide, so maybe we'll help again. You have a question? What is the u? It's just my variable. I just randomly assign the u to this gradient at the point. Here, it's this one. It's eta times u. Yeah. Okay. So I want to control how long the step will be. Because the gradient for the function will be always the same, but maybe I want to just, make shorter steps, so to say. So I'm still taking the gradient into account, but maybe multiply to some small constant. So maybe the theta will be in something like 0.001 until 1, right? So I'm taking much smaller steps. It's empirical constant. It's just, you can set it up. It's a hyperparameter, and it's telling like how large step I'm taking given the gradient. Does it answer a question? Okay. Any other questions? Great. So this is gradient descent, and now we can, how can we do that? Yes. Okay. So let's start. We start randomly, and let's start here. So this is point x1. I'm coming. So this is where I am. I compute the gradient here. So the gradient will be maybe sorry, not really. Maybe like that. It's not even better, but it's a line. You have to trust me. Okay, so this is a line. And what's the slope? Is it positive or negative here? It's negative, exactly. So I have negative slope. And then the update rule is xi plus 1 is equal to xy minus this theta times, let's call it u, right? The gradient. Since this is negative, so we'll end up with positive, and I'm gonna, the next step will be this plus the size of the gradient times some small constant. So I'm gonna move to the right. Ah, cool, this is great, this is what I wanted. I'm here, so doing the same step. Doing the tangent here. So the gradient is still negative. Okay, cool. And the gradient is bigger. So which means the next step will be not the same as here, but maybe a little bit larger, a little bit now here. Oh, now I'm here. And my gradient is going to be positive. So the whole thing will be here. I'm subtracting a thing. And the gradient is smaller. So maybe I'm jumping right here. Okay, and then maybe I will just jump before reaching the minimum. Does it make sense? Sounds easy. So what if we start here? What's going to happen? Yes?
We will find a local minima.
We find a local minima. Which one?
The left.
Yeah, maybe this one, right? If we start here, we maybe have no chance to reach here. Well, we might actually, if we have like super large learning rate, we might just, okay, here's my gradient, and the next step, and I'm going to just overshoot completely here, given this learning rate, and I might just, jumping left and right. That's why this learning parameter is time crucial, because it tells you like, are you going tiny steps? I mean, you can go really, 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 really tiny steps. It will just take a lot of time to minimize the function, or you might be overshooting. But here, typically, you would reach a local minimum. Is it a good thing or bad thing?
You want the global minima.
We want the global minima. So if you reach so everybody knows what's a global minima, local minima? Yeah, so global, it's like there's globally, there is no lower point for the function, and local is like, yeah, I mean, at some neighborhood of this point, this is a minimum. We want globally, I mean, we want a minimum of the function, we want a global one. Maybe sometimes the local one is good enough. Sometimes we're just happy with local minimum, right? So, but if we have a convex function, so convex function is something which is like that, then using this gradient-based optimization, we are guaranteed to end up here in the global one. If we have function which is like that crazy, then, well, you end up with some local minimum. Okay, any questions? Gradient-based optimization or derivative-based optimization for 1D function? Yes.
Random point we choose is the maximum, and the root is 0.
If you have 0, you get any troubles. Yes. Or, well, you might have, if you start, let me just delete this. So the question was, if you have maybe this function, and you start exactly here, so the derivative will be 0. Yeah, you're screwed. Start. I mean, yeah, start again. Or, well, what's the chance that you hit just basically the maximum? The chance is low. what might happen is that you will end up in some sort of valley. Oh, sorry, this is not a function. Wow, like that, and then there is like nothing happening, and then maybe there's a minimum. This could be a function. So you start here, go down here, and now the gradient will be 0, and you stuck here. You don't find a minimum. It can typically happen. So 0 gradient, bad thing. This would be like super crazy gradients, almost infinity, also bad thing. So you want to be somewhere in the, in between. Okay. Any other question?
So the algorithm stops when we reach a level where every x plus xi plus 1 is equal to the last xi, or?
Yeah, the algorithm stops when you decide to run over a compute. So you can, either you're really not decreasing anymore, or you reach a number of steps for which you're kind of repeating the whole thing. It's a design choice. You can always check like, well, is it my previous step? Is it still higher? Then I continue. But if your previous step was like lower, then you stop. Maybe yes. You can do random starts. Exactly. You can do several random starts. You can start maybe here first, and then if it fails, and then maybe here. And then you can try several runs with several random seeds and find which is one the minimum. You can do that. Yeah, you want a global minimum, but maybe you have to sacrifice a global minimum, go for a local minimum in some cases, which we'll see later on in training neural networks. Okay, so this doesn't guarantee you convergence. You can try sampling and stuff like that, but the functions we'll be optimizing are much more complicated. Okay. Any other question or point? Yes. I think it's called stochastic. I think it's called gradient descent. I would call it gradient descent because you take a gradient or derivative, and then you minimize the function based on the derivative. I would call it gradient descent. It's not stochastic gradient descent. It's not stochastic. Stochastic has a reasoning gradient descent. And stochastic gradient descent is typical for training in machine learning, sort of. Because the stochastic comes from sampling a random point. We're not there yet. This is just a taking derivative minimizing function, okay? We're not talking about deep learning today at all, which is a good thing. Because, typically, when I see lectures on function minimization on training with gradient descent, it's mixed with neural networks. And then it's like, oh, this layer and here, this is just, wow. You can completely decouple these things. You can minimize a function, and then we learn in the next part how to compute a gradient nicely, and then you just use it for deep learning. Okay, so let's move on. Now we get function of one dimension to another, but obviously the world is more complicated. So we have functions from n dimensions to a single number. Okay. An example of such a function? Well, I have a beautiful one. Anyone knows the name of this function? Never mind. I think it's called a Rosenbrock or Rosenbrock function. It's a very famous function which reads like that. So there's two hyperparameters. You don't have to remember. This is like a nice function because it's somehow shown to be hard for optimizing. Why is that so? Because it looks like a banana, sort of banana valley, and here's a minimum at 1, 1 is the minimum. And some techniques, which we are using kind of fail to find this minimum easily or fast enough and so on. So this is very famous function. By the way, if you want to have these plots, this is from Colab, and I put the links to this Colab plots to the lecture slides to the LaTeX. So if you want to play around with that, just go to the LaTeX source, and there's a Colab which I shared, so you can open it, okay? So this is a nice function, two variables, x and y, and then, we have 3D. Typically, we have much more dimensions. Now, we're coming from the simple derivatives to partial derivatives, okay? So what is partial derivative? It's directional derivative. So it always takes the direction of one of the dimensions, right? If we have two dimensions, there is one derivative in the direction of the one axis and derivative in the direction to the other axis, and with respect to a single variable. So now the terminology or the naming conventions are kind of hard. So we're using this weird symbol partial for the derivative. So partial derivative of f with respect to x2. This is how we write it, and this is how we read it. And if you have this function, for example, so this is x1 squared times x2 plus cosinus x3. So we have 3 dimensions. Can you visualize a function of three variables? No, unfortunately not, because we need like the 4th dimension for actually showing the output, right? So what we can visualize are 2 inputs, and the output is like kind of the surface, so we can kind of like visualize it and understand what it means. If you have 3 inputs, 3 dimensions and more, I can't do that. The human imagination is really bound to the world, 3 dimensions. So, and now how we do this kind of partial derivatives is basically we take each variable at a time and treat the rest as constants, right? So for example, the partial derivative with respect to x1 will be, so this is a constant, this is 0, so it will be x2, and then derivative of x1 squared is 2x1, so 2x1 x2, okay, and so on. So who hasn't heard of partial derivatives before? This is great. So partial derivatives, it's everybody knows that. Okay, good. So this is how we compute the partial derivatives per hand. And then we have a beautiful thing, which is called the gradient. Okay, so here's the example again. And we end up with derivative matrix or a vector, which is called the gradient of f. And this kind of ugly symbol is called nabla, or a gradient. So nabla is basically a vector of partial derivatives for each dimension. Okay. So we have 3 dimensions, and this is derivative, partial derivative with respect to the 1st dimension, to the 2nd dimension, and 3rd dimension. So here, the derivative of this function will be basically vector of these 3 small functions. Okay. Any questions? Good, because here the terminology is also kind of confusing, could be. So, yeah, okay, so what the properties of the gradient is that for any of these functions and every point x, the gradient points in the direction of the steepest ascent of f at the point x. Well, basically it's the same thing as we had with the 1 dimension. So the gradient or the derivative of 1 dimension is saying like, okay, here's how steep my function goes here at this point. Now we have, for example, in 2 dimensions. So the gradient is telling me I'm staying in a point somewhere in a hill, and the gradient is saying me, or not in a hill, in a valley. And the gradient is telling me, okay, you have to go that far. This direction is the steepest growth of this function in 2 dimensions. Okay, this is what the gradient is telling me at every point. Right? In 2 dimensions, it's easy to visualize. You're really sitting somewhere, staying in the valley, and just look. Okay, here's the steepest ascent. Sometimes we call the gradient the function is here. So this is the gradient, but this is not a real number. And sometimes we call it the vector of concrete numbers computed for the particular input. Okay, so this is something you need to somehow take the context into account, because the gradient could be a vector of numbers, which is basically the steepest ascent at the point, or it could be just how can I compute that? Okay, does it make sense? Yes.
So it says the steepest ascent of the point of multiple different ascents, and just defines the steepest of them.
Yeah, the gradient is the steepest ascent at the point, like the 1. This is the vector saying you, okay, you're here. This is my kind of the valley, and here this is the direction of the steepest ascent. Right? Yes.
Then also this local, right?
Yeah. I mean, you are at a point, and at the point there is one steepest ascent. Could be a different point pointing somewhere else, right? So it's local, exactly. It's a local change of the function.
Here we use the same method for finding a minima.
I'll go there. You're kind of okay. You're always like 2 steps before. That's great. So yes, and exactly, because now we can use it for finding the minima of the multidimensional function, because the gradient is just a It's the same thing as for one dimension, but we have it for multiple dimensions. So we can find a we can find a minimum of multivariate or multivariable function. And so we're looking for a vector or a position where the function has a minimum. So we do the same thing as before. We start somewhere random. So random vector, we have n dimensions. Then we compute the gradient at this point. So now this is the nabla thing. We have still the eta, this is the learning rate. And we update a step and go somewhere next. And after enough iteration or some stopping criterion, we have the minimum as we wanted. Okay? So because, I mean, and now you can really visualize it. Like you're staying, oh, maybe an example, right? You're staying somewhere. So this is the Rosenberg function, okay. You start somewhere here. So, which is like, this is the 3D and this is 2D. You're starting somewhere in this banana wally shape and you're in the middle of the mountain somewhere. And you say like, okay, so I cannot play a theater like the banana thing, but you know, you have to trust me, there's a banana valley here. And I'm staying on the side of the mountain and saying like, what is my biggest slope here? So it's to the mountain. Okay, I'm not gonna up. I'm going the other direction, which is the minus. I'm going down here and I'm just go down to the valley. So I did this large step because the gradient was huge here. So I'm just jump here, basically come here to the next little bit of hill in the middle of bananas. I'm saying, okay, what's the highest steep? Okay, so here I'm gonna do the other direction, downhill to the valley. And the gradient is getting smaller here, so I'm getting this next step and compute the gradient next step. And here I'm in the valley already, which means the gradient kind of vanishes. It's smaller and smaller, maybe almost zero, because it's almost flat. So at each step, I'm getting very small, tiny forwards to more minimum, more minimum, more minimum. And then I stopped here. Is it the final solution? No, this algorithm didn't make it. The true minimum is at 1, 1 for this function. But the gradient was so small here that my stopping criterion told me like, yeah, I had like 100 steps already, and now the changes are so minimal, I'm stopping here. Right. So this is why this function is hard to optimize. And it's known for being hard to optimize using standard techniques. Okay, so is the general idea clear? Why are we using the gradient and what is it telling me? Any questions? Great. Okay, so we know how to minimize a single variable function. We know how to minimize multiple variable function. So we had this gradient. What's still missing? We know how to do the gradient descent, but what we didn't touch really. Yeah, the step size is the learning rate, is a hyperparameter. Yes, we touched it a little bit. You can make it smaller, exactly. Yeah, we didn't touch it, but there is even much harder part. Is the the global minimum. I would kind of like, yeah, it would be nice to have, but maybe that's unnecessary, the global minimum. No, the point is that what happens when the functions are super heavily nested, like very nested deep functions, so to say, right? Because what we saw before was the Rosenberg beautiful function. You can do it by hand. Okay, example, we want to minimize this function with respect to W0, W1 to WK. Now, please, who said it? Can you write me a partial derivative? Okay, we need a gradient, right? We need a gradient for the output with respect to all these dimensions. So we have k dimensions and very complicated function, where it's not complicated, it has a name, and we want to find the gradient. Now, can you? Yeah, you can. It's wild. You can do like, okay, so it's a sum, then the logarithm, so it's like 1 over. Okay, then the sigmoid thing and the right. Depends on everything, like depends on the k, but you can do that. But it's it's getting nested. You don't want to do it by hand. Anyone remember? Anyone knows what the function is? Actually, I didn't make it up. It makes sense. It's one of the functions we can use in deep learning later on. So I think this is binary cross entropy loss for log linear function of k variables. It's very shallow, deep network in a way. It's just one layer network and a sigmoid on top of that. We come to that later, but this is the easiest function you might be optimizing, and it's still hard to kind of find the derivatives. Yes.
This is a recursive definition. Function E,
No. Why should be a recursive?
E on the right side. Define E.
Oh, good spot. Okay. Wow. No. Okay. So you know what? I wrote it with the exp. You know, I wrote it like the exponential function, but it didn't look so hard. So I made it look harder using the e number. So this could be like that. This is exponential function. Good catch. Okay, cool. So we want to compute a complicated gradients, right? We want the partial derivatives for complicated functions which are nested. So we need chain rule for multivariable functions, and it's getting very nesty now. So there are some rules which we should maybe know or not, or look it up, but there's rules how to do this partial derivatives for two functions. So let's say we have a variable t and two functions depending on the t, so h and g, and then there's one function z which takes these two functions together, and yeah, so this is the final function, right? This is a nested function of two inner functions depending on one variable. And we want to find a derivative or partial derivative of the final function with respect to this kind of the single variable. And we're gonna use it. This chain rule for multivariable functions. I mean, there's a proof for that. I'm not gonna go deeper into that, but just this is how it is. This is how it works. You can prove it. And it looks ugly. Why? Because we have this partial here, and we have the dx, and what is x? What is y? What is? This is what I meant by 1,000 different ways of writing partial derivatives, because you can write it as well as like that. So you say it's partial derivative of the f. So you're switching z to f to t, and then using the function names instead of the variable names, and it's correct as well. So that's why I guess like most of material of learning multivariate calculus or multivariate optimization is it's just hard to grasp how the author why partial of f and not for the output function and so on, because it's arbitrary. It's just one way to look at this, like this is Spanish and maybe this is French, and they're saying the same thing. It's just a different kind of naming conventions and stuff like that. So be aware of that, right? It's notation madness. But this is how you compute a composed function and the chain rule for that. So there is some multiplication and plus. And then if we have more variables, it's getting more complicated. So we have blah, blah, blah. I'm going to skip it right now because, I mean, these rules might be important to look it up because later on we will rely on them. So you've seen them before, but I don't want you to remember this. I mean, something that you perhaps not know. You don't need to remember, but know about it. Okay. So we have a chain rule. Why was the chain rule good, actually? Why was it good, the chain rule? Because we could like split the function into multiple parts and then multiply them together. And there's some plus as well, so we will be multiplying and stitching things together to get a gradient. Okay, cool. Let's try it. So let's try an example. We have still 25 minutes, so I think we'll finish on time. Everybody still with me on board? It's very ugly mathematics, but I think when we survive, you'll be equipped with understanding. So we have a function. So e here is a variable. Okay, this is not like the Euler's number. This is just a variable. E is a plus b times b plus 1. So we have two variables, and we want to compute the gradient with respect to a and b. So if I'm going to ask you, can you compute this by hand? Yes, easily. That's super easy. So you have the expression, blah, 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 and then gradient e to a is b plus 1 and so on. So this is like high school mathematics, easy. Okay? Well, but let's pretend it's more complicated function and do something much more fancy. So we're going to add, again, some intermediate variable and function names. So this is our function, a something, something times something, something. So we're going to call this function f1, and it will have two parameters, r and s, and this is r times s. So basically, We're just substituting. So this is going to be a product of two things. Then R is going to be our first parenthesis here, which is A plus B. And the S will be the second parenthesis, B plus 1. Okay? Everybody's with me? I mean, it's the same thing as we did before, just substituting and giving in names and making, it's small functions. So it's going to be a composition, basically, of addition and multiplication. Okay? So how can we represent it nicely in a way? We can use a thing called computational graph, where we basically say we have nodes in the graph, and this is it pink or red? So these pink things are the input variables, and these are the intermediate functions, and they compose to the output function, right? So everybody understands this graph, how it works? Basically here I'm saying, okay, R, my function is parameterized by A and B, and it was my A plus B function, right? So there was like the first parenthesis, basically. Kind of this. This one was the second parenthesis, and this is the multiplication. Okay, everybody understands the graph. So it's a direct, okay, A and B will be some concrete real numbers. Therefore, the R, S, and E will be also concrete numbers. So how do you evaluate this graph? How do you, if you're given A and B, how do you evaluate the E function? How do you go about it? Yeah, you can exactly. You need to use the topology of the graph. So you say, oh, S depends on B, then I evaluate R, and then I go to E. Or you can use something different. You can say, oh, give me E. But E says, well, I don't know R and S. So recursion, okay, give me R. Oh, I know A and B, cool. I'm coming back. Oh, S, I need this. Like basically recursion, and let it compute itself, like by calling the children of each node. This is basically a standard computational graph. So if you ever program a calculator, this is most likely what you ended up with, like small functions stitched together. Okay. So it's a direct acyclic graph, but it's not a tree as we saw before, because there could be like this diamond shapes. And each node is differential of the function with arguments. Okay, cool. And the leaves here are the variables or some constants. And this is the function composition. So the arrow is saying basically, yeah, I need this to compute, these are the arguments. And R and S are parents of B and A. Oh, sorry, R and S are parents. So this is parents of B, and B and A are children of R. Okay, so this shouldn't be any surprising. This is good. Why is this good? Okay, so let's start. We have this graph, and can we do something cool about it? So we can now compute each of these numbers, right? We know what S is, we know what R is, and we know what E is, right? We can do that. We just say compute everything, forward pass, the topology of the graph, or just recursion, okay? So we have these numbers. This is great. What's next? So now, because our goal is to compute the gradient of this function with respect to, so partial derivatives with respect to A and B, but we start at the top. So we want to compute the gradient for each node with respect to, to E, so the output. And we start here. So the partial derivative of E with respect to E is 1. This is something weird, but this is the starting point. Like it makes sense also like from calculus perspective. So you start here and saying, okay, this is 1. Why is it so? Because if you change E, how much is going to E change? Yeah, once. This is the starting point. So okay, this is the global output. So the global output is E with respect to node output, and node output is E as well. Yeah, this is boring. So what should we do next? For this node, we can compute the partial derivatives with respect to the arguments. So the arguments of this function f1 are R and S. So we're going to compute partial derivative of E to R, or with respect to R, and partial derivative of E with respect to S. Can we compute that? Can we compute what is derivative of e to r. So our function is r times s, right? So what is going to be the derivative with respect to r? S, exactly. And what is going to be derivative of e to s? R, yes, exactly. We just do the simple function and compute the derivatives here. We can do that. So we know how to compute these things. By the way, these will be real numbers, right? I mean, this is just how we compute them, but at the end of the day, these will be some real numbers. All right, so yeah, let's move on. Oh, by the way, we know what S and R is because we just computed them already before in the forward pass. So we're just gonna reuse the computation. We don't have to compute them again. You know, we store it here. Oh, okay, this is gonna save some time. Everybody's with me in this step? Local derivations with respect to the arguments of the function. Now we're moving next and we're saying, okay, let's look at the children of this E node. So let's start maybe with R. And again, I'm gonna compute the global derivative, so the partial of E with respect to this output of this function with respect to R. And now what's kicking in is the chain rule, right? Because I know that E is a compose of F1 and R is in there. So I'm gonna use the chain rule and just basically multiply these partial derivatives. So this is where the chain rule of multivariate calculus comes in, and I'm using that for computing this sort of gradient, this partial derivative, excuse me. And you might be wondering, oh, well, I'm computing E, partial derivative of E with respect to R, I have it here already. Yeah, this here it makes no sense, but later on we'll see it will make a lot of sense. But now actually I can reuse the same value here, but I'm just going to compute. What I need for this computation is the parent, it's coming from here, times the local derivative from here. This is the chain rule in praxis. Okay, so I can compute it. Very cool. So I'm moving next to next child of E, and I'm going to do the same thing. So I'm going to compute partial derivative of E with respect to S, which is the parent times the local. This is a chain rule. Okay, everybody's with me? Why we do this? And it's also nicely graphically. I'm taking like the derivative of the parent multiplied by the path, and this is how I get the derivative of this point. This is pretty cool. Okay, sounds great. So what's the next step? What we're looking now? Where should we go? What should we avoid next? So yeah, we started on top and got this thing. Then we computed the local derivatives of this function, of this node. We're here, get a global, here get a global. So maybe we should go deeper here and compute the partial derivatives of this function with respect to its arguments. So again, this function, f2 of a and b, is a plus b. Okay, so, and now the parents are the children are a and b. So what is going to be the derivative of r with respect to a? What is the partial derivative of r with respect to a if this function is this one? It's going to be 1. Sorry? Yes, 1. Exactly, because b is a constant, so it's 0, and a is going to be 1. Okay, good. What's going to be the derivative of r with respect to b? 1 as well. Yes, exactly. Right? So this is a local function. We can how to compute the derivatives, right? This is very easy. So I ended up with these derivatives, and okay, this is cool. I'm gonna go deeper now, and I'm taking the child of r, which is going to be a. And now I'm gonna compute again the same thing. So global output with respect to this node output, and this node is already the input, so this node output is given. And then again, I'm using what I'm using here. So dE of with respect to r, which I computed before. Okay, I'm taking just the derivative, the parent thing, and again multiplying by the transition here, by the local derivative. So basically, I'm always taking the parent's global derivative by multiplying the local derivative. That's all I do all the time. And here, voila, what we have? We have partial derivative of E with respect to A. This is what we wanted. This is, I mean, we wanted to compute the gradient. This is one part of the gradient, right? This is one of the variables, and we have the gradient of the output given the input. So this is cool. Let's finish. So the next step is, obviously, we're going to look at the children of S node. And here, again, we have a partial derivative of S with respect to B, which is going to be, okay, what is this function? F3, B plus 1. So what is this going to be? Equal to 1, exactly. Well, very easy. Okay, so we have that. And now what's the last point in our recursion, how we travel in the graph is the B. And now we're going to compute. Okay, so we want the global with respect to this node. And here, this node has two parents, right? So what I'm going to do is to use this rule for chain rule for multivariate functions with multiple parent nodes. And basically, I'm taking here the one parent times the transition plus the other parent times this transition derivative and stitching them together. So this is the multivariable chain rule. And this is how I ended up with the gradient. Oh, it's very kind of complicated, clumsy, and so on. But are you still with me? Everybody kind of could follow what we're doing here. Very tiny steps. We are interested in the global derivative with respect to something which is on the nodes. And the way we got there is just applying the chain rule on each of these sub nodes and going by the next children, the next children, the next children. And now, voila, we ended up with the gradient of this function with respect to A and B. This is the gradient of the function. And basically these are numbers now, because we had A and B were real numbers, these were real numbers, this was real numbers, all the gradients were real numbers, so we ended up with a vector of real numbers. So we kind of evaluated the gradient of this function at points A and B. In a very weird way, but at the same time, in a very cool way. Because we are clever. We didn't do it like, oh, you have to compute a gradient per hand and make it like formula. We are just transferring first from the bottom up, computing all the outputs of each of the node, and then from the top to bottom to find the gradients in order to get the gradient of the input nodes as the result. This is what we wanted. And by caching, yes, I get you. By caching the intermediate values, we're just reusing them all the time. Yes.
What's the WRT stand for? What does it stand?
W with respect to, okay, sorry. WRT is with respect to. Okay. So we're having global global partial derivative with respect to the node outputs. This is what it means. Okay. Any other question to this? Is it maybe it doesn't spark a joy, but this is how basically how everything works under the hood. It's called, how's it called? I don't know. Maybe we'll get to that. Okay, so now what is actually, so we did just very tiny little things for each of the node. We build a computational graph and then computed the gradient. So a generic node in a computational graph can have multiple parents here and multiple arguments, right? So this is what we have locally, and maybe it goes somewhere here to the output. And this function, what we need to compute is that if we have the output here will be E, not the Euler's number, but just E as a maybe error. Then we need to take all the parents of this node, all the parents, and multiply by their transition derivatives. Sorry, it's not transition derivatives, it's derivatives with respect to this function output. Right? That's what we did. It's just we're summing up over all parents of this node and their global derivatives times this, the local derivative, and it's chain rule for this node, right? And then we can compute also for each node, we can compute again their local derivatives with respect to its children, right? And we are doing recursively with that in the topology of the graph, and we end up with all the global gradients to each node, including the inputs. So which means if we want to implement this, each of the nodes must be a function which we need to compute the output value of this function. Yeah, it makes sense. I mean, function typically has to output a value. So we can do that. And we have to know how to compute the partial derivatives with respect to its function parameters. So if we have a function of ABCD, we have to know how to evaluate the function for ABCD and how to compute partial derivatives with respect to A, with respect to B, C, and D. What we just did is called backpropagation or reverse mode differentiation. And it has two parts. So one is the forward computation. Basically, we compute all nodes' output, and we store it there because we're going to use it for the gradients. And then we started from top and computed the overall function partial derivatives with respect to each node. And that's it. This is how you find a gradient of very super complicated function, including the, what I showed before. Yeah, I mean, this, can you turn this into computational graph? Yes, you can. It's just stitching functions together. So you say, okay, I have a function which is sum of this will be a product, there will be a logarithm, then this will be arguments, and so on and so on. I mean, it's not trivial, but it's fairly easy to get a graph of this function, and then compute, basically use the backpropagation to compute a gradient for every input. Okay. So where did I stop here? This backpropagation. So recap: we can express any arbitrarily complicated function from multiple dimensions to one dimension as a computational graph. We can do that, absolutely. Right? We can parse the function as humans and make it a graph. And these nodes will be maybe easy function, which you know how to make a derivative with respect to its inputs. And then for computing gradient at concrete point, we run the forward pass and the backpropagation. And when we are caching each intermediate output of each node, we avoid repeating computations, and then this is like efficient algorithm for finding the gradient of a function at a certain point. Any questions? Will you be able now to implement minimizing a function of, let's say, the Rosenbrock or this kind of very nested function? Will you be able to do that? I guess so. I think you have everything you need to do to implement it. Well, there's tricks. You need to find, you need a way how to compute this, how to build a graph, the computational graph. Yeah, but if you're doing, I don't know, like in Python or object-oriented, you make a node and stitch them together, like parent-node relationship. So you can build a graph. Then it's easy. You need a topology. Or you can take each node, each function, and make the topology per hand. You say, okay, the ordering of the nodes is like that. So you know where to start with. So you would say maybe for this input, you would say, okay, the topology will be A, B, R, S, E. And then you know how to evaluate, in a loop. So that's also easy. That's possible. So I guess, that should be possible to do. Is it? I know. And then the devil is in the detail, how to make it efficient and bug-free and so on. But basically, this is it. So we can quite efficiently find a minimum of any differentially nested multivariate function. This is what we learned today. We have multivariate nested function, very deep, very complicated, different paths and so on. So it's not a tree, it's really like a graph. And we can find the minimum. How? Well, we have this gradient descent, which takes you at each point to the best next solution. It's local move. And then, so this is the easy part, this is the gradient kind of descent, like, okay, I need a gradient here and I'm coming the next step. How to compute the gradient for this each point? Yeah, we're using backprop. So you can effectively compute the gradient automatically without like writing on the paper this complicated function and what's the analytical solution to this, the partial derivative with respect to that partial derivative. You don't need that. You just need all these tiny functions have to be differentiable. You have to know how to create their partial derivatives, but that's all. And the function composition will just work out of box. We didn't touch neural networks at all, which is a good thing. I think it's a really good thing because it comes with a lot of, a lot of terminology and a lot of kind of their own naming conventions and matrices and things like that. And I think it makes it super complicated to understand to understand gradient descent and backprop, because backprop is just a general way of computing gradients for multivariate functions. It has nothing to do with neural networks. It just works for neural networks to train them well and effectively. But you can do, if you do, I know, where would you do like minimizing functions, like in physics, in some, did you do any function minimization before somewhere? Where? Math? Okay, yeah, okay, cool. Like numerical mathematics, right? In numerical mathematics, you have multiple ways of minimizing function. I think this is actually called conjugate gradient descent. Mathematically correct, maybe. You have numerical methods, and now you have one which is kind of very good for multivariate functions, and you can find a minimum. Yeah, that's cool. It will be super useful next lecture for training neural networks, because neural networks are just complicated functions, nothing more. Okay, any question? Very good. Thanks a lot. I'll see you next week.